In theory, the sunlight the world receives in just a few hours packs enough energy to fuel the planet for an entire year. In practice, however, it's not that straightforward. One problem has been that conventional silicon solar panels have only been able to convert a fraction of that light into electricity. It's a complex problem. There isn't space for solar panels everywhere, but we can make them more efficient. And that could be key to boosting renewable energy and cutting emissions. New innovations and materials are supercharging light-powered cells of all sizes, like the panels emerging from this factory outside Berlin.
Silicon's been around since 1954. They've kind of done everything they can do, although it's amazing how much they squeeze out that last bit of efficiency. I said to myself, what could we do to enhance the silicon to make it more attractive?
The company's answer was to combine silicon with their version of a crystalline semiconductor material collectively known as perovskite.
You can adjust its composition, you tinker with the components, the chemicals that are inside. You can change where in the solar spectrum it absorbs best.
It's taken a decade of tinkering to perfect a viable way to combine these silicon wafers with perovskite. And the company claims it's the first to do it on a commercial scale. Much of the process occurs behind closed doors. Perovskite can be notoriously difficult to work with. It typically contains toxic metals and can be unstable and vulnerable to heat. Not ideal traits for solar panels supposed to last for decades.
But we worked in such a way to effectively strengthen or toughen the material for temperature. And we now have a solar cell, looks and feels like a silicon solar cell with the distinction it produces 20% or more power.
The company claims that over the long term, that extra output more than compensates for the higher price of tandem cells, which can cost 20 to 50% more than conventional silicon panels.
We know that because our customers are telling us they're prepared to pay more on a per panel basis. They know the math that if you get more efficiency from those panels versus the overall system cost, the energy is cheaper with us, even if they pay a bit more for the panel. And that allowed us to be the first to ship commercial product to a utility in the US last year.
Perovskite cells are still new to a market where silicon panels make up the vast majority of those used for industrial power generation. How excited or interested are you in developing technologies like perovskite?
We're excited at the potential of it. Probably more attractive for commercial industrial applications where space is tighter.
Space is less of a problem at this sprawling solar farm on a former landfill site east of London. And that's one reason why the asset manager operating it has no immediate plans to add perovskite panels into the field.
There is, of course, the balance to watch the degradation rates of perovskite and the cost of perovskite to see how it goes. But the potential of a 30% efficiency, it's very attractive.
That attraction extends beyond the commercial sector to government-backed facilities like this Clean Energy Centre in Berlin. Here, experts in ultra-thin, flexible photovoltaics have extracted record-high light-to-electricity conversions from perovskites, albeit at small laboratory scales.
We're now trying to in-depth understand what makes these materials so good.
And it's investigating other potentially groundbreaking qualities in these sometimes delicate, sometimes robust minerals.
They can recover performance. So if silicon breaks down and goes down in performance, it cannot heal itself. A perovskite apparently can. It's incredibly mysterious. We are entering a new paradigm in solar energy material research.
While materials like perovskite are mainly developed for industrial utility-scale generation, other innovations are coming in smaller packages, like the paper-thin photovoltaic cells able to be moulded into just about any device emerging from this factory in Stockholm.
All printed, silicon-free, no toxic materials, no rare earth metals, nothing like that. It can take any kind of light, indoor and outdoor, and convert it to electricity. We apply it to stuff like headphones, wireless speakers, hearing protectors, remote controls, sensors, smart helmets.
The cells turn light into electricity via the company's unique invention, a nanoparticle ink that absorbs light and releases electrons, generating an electric current.
This is our conductive layer, the magic source of the solar cell. That can be printed onto anything and printed with this very normal screen printing technology.
It's still a relatively niche market, and these cells can't sustain power-hungry devices like smartphones and laptops alone. But they are charging hundreds of thousands of other electronic gadgets.
In terms of avoiding electronic waste, you don't need charge cables or charge plugs. You don't need to manufacture billions of batteries. It's also about changing a behavior. As a whole generation grows up now, realizing, okay, I have light, so I have power.
Solar power remains the fastest growing source of renewable energy. And whatever the scale, new technologies are inspiring confidence, despite resurgent support for fossil fuels in countries like the US, where subsidies for clean energy are being rolled back, and a market-disrupting oversupply of conventional silicon panels from China.
The reality is we need lots more PV to deliver the energy transition. Much more than actually the current oversupply, probably 2 to 4 times more manufacturing capacity is really needed.
I'm really excited about the technological progress because in the end, economic interest will be a much better and more efficient driver than doing the right thing.
In the end, money talks. So it's going to happen.